Okay, welcome to Math 158, Functions, Graphs, and Matrices. This section is section 2.4. It's on logistic functions and models. Compared to some of the recent videos, this one will be a little bit shorter, okay? We're going to take a minute and look at the logistic function. What do we mean by a logistic function, okay? So there's a little description here. I can read most of it to you, but doesn't always make the most sense first read through, right? A logistic function is a function that is in the form f of x equals n divided by 1 plus a times b to the negative x power. Okay, the graph of a logistic function is an S-shaped curve sandwiched between the horizontal lines y equals 0, y equals n, where n is called the limiting value of the logistic curve. Okay, so let me give you some examples of things that might follow a logistic curve. Okay, let me come over here to a blank part of my screen. Suppose that we were to look at a coordinate plane, right? We're going to track the number of iPhone sales, okay? And the iPhone comes out and more people, few people can afford it. They start to get it. And all of a sudden, more people get excited and more people start to buy the iPhone. And the regression analysis, the growth in sales of the iPhone appears to be exponential growth. Okay, and we got all excited about the increase in iPhone sales is exponential, and we could talk about a video game system. We could talk about what percentage of the population has broadband internet, what percentage of the population is getting vaccine for whatever may be going on, and the growth rate appears to be exponential. But what happens in a lot of places is we talk about the number of people buying an iPhone is here's a rate of fastest growth, but then it starts to slow down because the number of people buying an iPhone, we're going to soon reach the point where everybody who wants an iPhone has an iPhone. And that's why now we're on the iPhone 12 or 75 or wherever we're at. So you'll notice in my description, we said that the graph is an S-shaped curve. This is kind of an S-shaped curve. We're going to have a horizontal asymptote that is the x-axis, y equals 0. And then there's going to be a horizontal line here, which is y equals capital N. And what n is called is n is a limiting factor. Okay? If you think about a town, okay, go back to the 1910s, and in your particular town, there are so many people living in the town, and population starts to increase, and it looks like the population in your town, let's do this again, it looks like the population in your town may have been hovering around this x-axis, y equals 0, and hovering and growing and growing and growing. What happened is all of a sudden population starts to take off and increase exponentially. You think about this as a town that used to be a farming community, and people start selling their farms and becomes more suburban, and the population growth rate of the town continues to increase exponentially. Well, the amount of people living in a town cannot continue to rise exponentially. It may continue to appear to rise exponential for a period of time, but what has happened in a lot of New England towns, around Boston, around Hartford, around the area, is we've pretty much maxed them out. Okay, even around Hartford, little tiny towns like Wethersfield or Newington may be fairly maxed out, and the growth rate starts to slow. Okay, and we reach this limiting factor. I'm going to draw it again, so my graphs are going to look about the same. I've got another horizontal axis, y equals capital N, where n is that limiting factor. That's the maximum population that town can sustain. Now, notice that the graph may start, keep inching up. Even in a town like Newington, we might build a couple of new houses here and there from year to year. But we're going to reach that maximum population. And there's lots of examples we can come up with, right? So you've got a lake and there's no fish in the lake really. So you stock a couple of fish in the lake and the population takes off. Okay. And the population appears to be increasing exponentially. but the lake can only sustain a certain population of fish. Okay, so there's a number of examples like that. Okay, so there's a couple examples that I'm going to use here. First of all, we're going to look at this one where we're going to model here. A flu epidemic is spreading through the United States population. Okay, interesting timing. Right, this video occurs during the COVID-19 pandemic, and hopefully we're out of this soon. But you've got a flu epidemic is spreading through the United States population. And for this particular flu epidemic, we're going to say that an estimated 150 million people are susceptible to this particular strain. Okay, there's certain predictions, certain estimates we're going to make. It's predicted that all susceptible people will eventually become infected to some extent, to some degree or other. But we're going to assume that all the susceptible people will eventually become infected. That's my limiting factor, by the way. Okay, so if I've got the expectation that we're going to see this increase, okay, until we reach our maximum, we're going to inch closer and closer and closer to that maximum of y equals n, which is 150 million people. Okay. Currently, okay, at time t equals 0, let's say time t equals 0 right here, right? So we're at the point we're starting, this is the line y equals 0, right? That's always our bottom horizontal line here. So at this point right here, at time t equals 0, that does not mean when the infection started. That means at the point we start observing the behavior of the virus. So at time t equals 0, there are 10,000 people already infected. And we notice that the number of people infected is doubling every 2 weeks. So my x-axis, okay, so x is equal to time in weeks. Okay, y is equal to the population infected. And I'm sure you can read that really well. So 2 weeks in, after we started observing, the number of people infected has doubled. So now there are 20,000 people infected. Okay, so now we're going to use this to come up with our model. And see, this is what the model looks like. P of t, the population or number of people infected after t, in this case, our time is measured in weeks, is equal to n, which is our limiting factor. In this case, we set it to the 150 million. 1 plus a, we're going to have to figure out what that a is, times b, we're going to have to figure out what the b is, to the negative t. So first of all, P of t is going to equal the population, the maximum we expect to reach was 150 million. 1 plus a times b to the negative t. Now to compute our a value, what we're going to do is we're going to take our first point, 0, 10,000, okay? We're going to take that point 0, 10,000, and we're going to substitute that 10,000 in for P of t and 0 for t. So 10,000 equals 150 million divided by 1 plus a. Now b to the negative 0 power, that's equal to b to the 0, which is 1, and 1 times a is a. Okay, so now if I'm going to solve this, we're going to have multiply both sides by the 1 plus a. So I've got 10,000 times 1 plus a equals 150 million. So 1 plus a, what I'm going to do here is I'm going to divide by the 10,000. So let me move this down here. So 1 plus a will equal 15,000. And subtract 1, so A is equal to 14,999. So what I'm doing is I'm trying to build that function. So now I know that P of T is equal to N. Remember that N was 150 million. 1 plus A is 14,999 times B to the negative T. Okay, now the way that we're going to find the B value, there are two ways to find the B value. And I'll show you both ways that we can do it. One way would be okay, so now we're going to find our B value. And there's a couple ways that we can find our B value. One way to find the B value would be to say, let's take that second point. Let me come back up here. Remember this second point to 20,000. So 2 weeks in, there are 20,000 people that are infected. So my P of T would be 20,000 equals 150 million people over 1 plus 14,999 times B to the negative 2. So I'm going to multiply both sides by this denominator. Didn't leave myself much room there. 1 plus 14,999 B to the negative second. Multiply both sides by that, and so we're going to have 20,000 times 1 plus 14,999 B to the negative second equals 150 million. Now I'm going to divide both sides by the 20,000, and 1 plus 14,999 B to the negative second is equal to 150 million divided by 20,000, which is 7,500. You can check that on the calculator. Subtract the 1 from both sides, and 14,999 B to the negative second equals 74.99. I'm going to keep going off my page. Now when I divide both sides by the 14,999, we have B to the negative second equals 74.99 over 14,999. And you have a couple of options on what you can do here. If I just want to go straight to my calculator and kind of use that, right, I need to have B to the first, so I would raise both sides to the negative 1/2 power. And I could just do that, right, 74.99. Actually, let's put this in parentheses. 74.99 divided by 14,999 to the negative 1/2 power, and we get 1.414. Okay. Now, so that's my B value. Another way I could have gotten my B value is I could have said, I'm going to move to the left here. It appears since we started at 0, 10,000, 2 weeks later we've doubled. And remember that this begins following an exponential pattern. So we can estimate using the exponential function y equals little a times b to the x. And 10,000 is our initial value, our value of y when x is 0. So that would be a. Then I can put 2 and 20,000 in for x and y. So 20,000 equals 10,000 times b squared. So b squared equals 2. And if I take the square root of 2, Notice I don't have the exact same value, but it's pretty darn close because that 14,999 divided by 75, I'll be okay, 74.99, slightly more than 2. So we still get B as approximately 1.414. So there's two different ways I can get my B value. So in any case now, I'm going to take my B value. Where do we go? Take that B value, we're going to substitute that back in. And so P of T will equal 150 million over 1 plus 14,999. Oops, not B, right? What is B? B is 1.414 to the negative T. And this is the logistic function. Okay, now before I do anything else with that, I'm going to put that in my calculator. That's going to be 150 million divided by, use parentheses, 1 plus 14,999 times 1.414 to the negative x. And then I'm going to close that parenthesis for the denominator. Now I can try to graph that, but I'm probably not going to see anything, right? Because we're starting at 14,000, or we're starting at 10,000 and going up from there. So my x min needs to be pretty close to 0, and my x max needs to be at least 150. Let's make it 160 million people. Okay, and let's let the, oops, I'm sorry, no, that's y. Y is going to go from 0 to 160 million. X will be my time in weeks. So let's go from negative 10 to 52 weeks, just so that that's a year. And let's graph that and see we have this S-shaped curve. Okay. Now the question that I'm asking here is to use the model to predict to the nearest week when 1 million people will be infected. Well, before I do that, remember going to second calculate, we can do a value, right? Initially, 10,000 people were infected. 2 weeks later, almost 20,000 people. A month in, 40,000. What about 10 weeks into the flu epidemic? And notice we're about 318,000 people. What about 20 weeks in? Okay, you can see that this is starting to increase. So I can figure out 6 months in. Well, 6 months in is 26 weeks. Where are we? And we're at about, is that 52 million people? 52,851,000 people that have been infected. If my question is to the nearest week, when would I expect 1 million people to be infected? I'm going to use a strategy like I've shown you in a previous video. I'm going to let Y2 equal 1 million people. Okay, now they don't look very different, okay, because my window is going up to 160 million. Okay, if I were to reduce this just a little bit, I'm going to take out a 0. So we're going up to 16 million. So I'm not going to see as much of the graph, but I can see how many weeks in we're going to hit 1 million people. Second, calculate. Remember number 5, that point of intersection between the first curve and the second curve, and that's a reasonable guess. It will take about 13 weeks. So about 13 weeks in, we would expect 1 million people to be infected. Okay. Now this would be if I'm going off of information like this, I've got those 2 points that initially at this point, this is what I see, and then 2 weeks later, I see 20,000 people infected. So there's a lot of algebra there. Okay, I suggest that you review that. You make sure that you can do some of this algebra. Okay, especially getting the B value is a very good skill to have. But now if I look at this problem, okay, number 2, this table shows the percentage of US homes with wired broadband connection as a function of time in years where t equals 0 represents the year 2000. So 2 is year 2002, 2003, and the percentage of homes, this is the percentage of homes with broadband internet connection, and we can see what was going on from 2000 to 2013, 2002 to 2013. A, find the best logistic model for the data. Okay, now I'm not going to assume, by the way, like I did in the previous problem, that all 100% of people are going to get broadband internet. Okay, there may be other options available to people that they choose. So we're just going to look at this data. So the way I'm going to do this, okay, I'm going to clear these things out, is just like we've done the linear regression, quadratic regression, exponential regression, logarithmic regression, calc, edit, and I'm going to put in my x values or my t values into L1. So that's 2, 3, 4, 5, 6, 7, 8, 9, 10, go to 13 to 11, 12, and 13. My y values are 6.7, my fat fingers there, 9.6, 12.8, 16.4, 20.3, 23.2. This to me is the most boring part. And 29.8. Okay, so there's the data. Let's do a scatter plot of the data. So we're going to go to a second stat plot. I'm going to go to plot 1. I'm going to turn it on and make sure that my X list is L1. My Y list is L2. So I got to make sure that those are right. I'm going to switch this to a plus because I like that better. And now I'm just going to hit a zoom zoom 9. Okay. So I don't know. It kind of looks like the data is curving upward here. It reaches a point and starts to curve down. So that to me looks like it could be a little bit logistic. So if I want to find the best logistic model for the data, I'm going to use my calculator. This is certainly an option. Stat, calc, and I'm going to go down and be careful that you don't confuse. Now ln number 9 is the logarithmic, and I like the fact that they use ln so I don't get logarithmic and logistic confused, right? So ln is the logarithmic regression. Number B here is the logistic regression, right? Don't keep going. Logistic regression. X list is an L1. My Y list is an L2. And yep, let's go ahead and store that regression equation into Y1. Remember that to store that regression equation is alpha F4 number 1. And then we're going to calculate. And it takes a minute. Okay, now the calculator gives the results a little bit different than that B, like in the previous problem. Okay, so notice that the function here, the calculator indicates that it's y equals c divided by 1 plus a times e to the negative bx. So in the previous problem, right, in this function here, we say that this is a b value, and over here we say that it's e to the b. It's don't sweat it. Just make sure that with the calculator you put the correct values in the correct place. C is 29.23. Now C is my numerator. That's my limiting factor, okay? So it's a little odd here that the maximum is 29.8, but the function predicts that 29.2 is the maximum we're going to reach. That happens every once in a while. 1 plus A is 8.998 times E to the negative B 0.4937x. So that is the best logistics model. At this point, I'm suggesting that you write it, okay? What percentage of homes does the model predict will have wired broadband? The model predicts 29.23%. That's my limiting factor. That's my top. And again, this is an odd example where that 29.8 is slightly larger, okay? That does happen from time to time, okay? Because that's what the model is predicting. Now, before I answer C, in what year would you expect the percentage to reach 15%? Let's go ahead and remember, because we did store reg EQ, this equation is already in Y1. So when I press graph, I can see the logistic function on top of those data points. Now I could use this to say, according to this model, what would I predict broadband connection to be in 2020? Well, that, remember, would be year 20. Whoops, we've had this before. Calculator screaming at us. We're going to hit go to, right? Because in our window, our X values are only going up to 14. Let's go at least out to 2025. Notice how that levels off. So calculate that value again. In 2020, the model would predict 29.22% of homes. In 2021, 29.23% of homes would be predicted to have broadband internet. For C, in what year would I expect the percentage to reach 15%? Again, I'm going to go to Y equals, and I'm going to let Y2 equal 15%. And now I'm going to look for the point where those two graphs intersect. Second calc, number 5. The point of intersection is the blue one, my first curve, sure, so press enter. Yep, the red one's my second curve. That's a good guess. So I would predict 4.6 years after after the year 2000. So that's about 6/10 of the year after 2004. Okay, so that would be during the year 2005. Okay, perfectly fine, in my opinion, to use the calculator for computing these. That's a reason we've developed the technology. You want to be able to use both together in tandem. Okay, so there's just a quick look at logistic regression models.